All right, this is the section on differentiability and continuity. Our first video, which is sort of the second video, is going to be on differentiability. If you can guess what the next video is going to be on, you get some bonus points. All right, no actual bonus points, but maybe some brownie points. Okay, so differentiability, in short, something is differentiable if it has a derivative. Something's not differentiable if it doesn't have a derivative. So let's talk about what that means. So let's remember a couple things first. So remember that one of the big points that I want you to remember is that the derivative of a function is the slope of the graph. All right, so the derivative at a specific point is the slope there, slope of the tangent line. The derivative function is the slope function. It tells you the slope of the graph at any point. All right. And remember that we also learned in the last section, much to the chagrin of some of you, I'm sure, that the derivative can also be written as f prime of x is equal to the limit as h goes to 0. Yeah, you remember this guy, f of x plus h minus f of x all over h. So if this limit exists, if this slope exists, then we have differentiability. If not, then we don't. Okay? So let's summarize that. Get that down in writing as well. If this, remember we learned this in the last video, dne does not exist. If this does not exist, and specifically, let's say if this does not exist at a specific point, then f is not differentiable at that point. I really love abbreviations, but maybe it's a little early to use them all the time. This means differentiable. Okay. So that's, in short, what differentiability means. So let's see what it looks like now, because honestly, definitions are all great, but this really is a class about applications. This is a class about seeing things and doing things, at least in theory. At least in theory. So I'm going to show you what this looks like. Okay. Some examples. Let's look at a function over here. And let's say this function kind of looks like a parabola. And then it turns into a line. If this is the point where x is equal to a, we would say this is not differentiable at x equals a. Okay, so not differentiable at x equals a. Now everywhere else on this function is differentiable. This function is differentiable in infinitely many places. The only place it's not differentiable is right here, because what's happening, right? On the left part, it kind of looks like this is our tangent line, right? But from the right part, it kind of looks like this is our tangent line. So there is no limit. The limit behaves differently on the left. It behaves differently on the right. So there is no limit. The limit doesn't exist. There is no tangent line right here. No tangent line. So we say it's not differentiable. All right. In fact, anywhere where there's like a sharp curve like this, it's not going to be differentiable. So another example of this is if we had a function like so. And let's say it look like this. Again, at this point right here, it is not differentiable either. This is actually not the same situation. This is what's called a cusp. And the reason why it's not differentiable is look at the slope of the tangent line. The tangent line is vertical here, and the slope of a vertical line doesn't exist. So this is another thing Sometimes these are called, this one over here is called an edge. All right, and this one over, the second one's called a cusp. Then there's, you know, other things as well. Let's say, you know, we were looking at, oh yeah, this is a common function that we've done stuff with. This is the absolute value function. This is also not differentiable right there. Again, there is no, the limit does not exist. So again, if this is a, this is also not differentiable. That's sort of like what it looks like. And the idea is, can you find a tangent line here? Is there a tangent line at that point? If so, great, it's differentiable. If not, nope. And these are the common things, edges and cusps. There are some other situations as well, but these are the ones we're really going to see in this section. All right, so let's do an example and then we'll be done with this video. We'll use the next page. Example 1. Is f differentiable at x equals 1, where f of x is equal to the piecewise function that's defined to be x for every single point other than 1. And it's defined to be 2 when x is equal to 1. So again, it's very, very important that you have a mastery of piecewise functions for this section and for future sections as well. If you feel uncomfortable with them, go back to 1.5a. That has a link to an older video for another class. I say older, it was last semester, for another class where I talk about piecewise functions for as long as you may need. So we're going to graph this and see what it looks like. Okay? And see if it's differentiable at this point. So, do our best graph here. And see what things look like. Remember, for piecewise functions, you mostly just graph each individual piece, and then you erase everywhere that it says to erase. So remember, the line y equals x is just, it's not that. That's for sure. The diagonal line through the origin. All right. And we use this line, remember, piecewise function. We use this piece everywhere except when x is equal to +1. So we're going to erase everything that's not in the domain. When x is equal to +1, we're not on this graph. We're going to denote that with an open circle. All right. So that's the first piece. Now to finish graphing this piecewise function, we graph the second piece. All right. And the second piece is just the point when x is equal to 1, y is equal to 2. When x is equal to 1, y is equal to 2, and we have successfully graphed this piecewise function. We'll talk about this more in the next video on why this is not differentiable when x is equal to 1. It's not even continuous at x equals 1, which is the next video. All right, so it sort of looks like there'd be a tangent line, right? It sort of looks like the tangent line's right here, but the problem is it would have to actually be up here because the point's up there, so we just have some real problems in this one. This is another case of an example for something that's not differentiable. In addition to the previous cases that I showed, this is one more case of something that is not differentiable. So our answer is going to be no. All right, so for all of these problems like this in the homework, just graph the piecewise function and then use what we know about differentiability and continuity. And remember, if you always want to see some more examples, the book has some good examples before the problem sets that are usually pretty similar to homework problems. This one actually, it's not very similar, but in general, they are pretty good. Okay, so that's the video. Let me know if you have questions, and then next video we'll talk about continuity. Good luck.